I'd like to go back to a scalar differential equation. And I'm going to go back to using x as the independent variable. Not that I couldn't use t, but just for some variety. Some differential equations are better thought of where the independent variable is x, maybe representing a distance instead of time t. I'm going to let dy dx be y squared. I'm going to first solve this by separating variables. It's different, actually, than most of our examples where we separated variables. Something different happens. Then I'd like to think a little bit more clearly, hopefully, about why separation of variables works. And the key to seeing why it works is actually to use ordinary function notation rather than Leibniz notation. It's kind of the key to seeing why separation of variables works. Then we also will talk about drawing the slope field, thinking about an equilibrium solution, in fact, at y equals 0. And also noticing something interesting about solutions. They actually have vertical asymptotes, which might seem kind of strange if this is going to be an accurate model of reality. But let's go ahead and solve this by separating variables. It's something, an example of the type you should be able to do. The variables are x and y. You get all the y's on the left and all the x's on the right, meaning divide both sides by y squared and pretend, quote unquote, to multiply both sides by dx. I could rewrite this as dy over y squared equals dx. Or for purposes of integration, maybe it's better to write it as y to the negative 2 dy equals dx. And yeah, now we would integrate both sides. Before integrating, right away here, let's actually talk about another approach to this that's maybe a little bit more clear, where we don't have to pretend this thing is a fraction and pretend like we're multiplying both sides by dx. Probably a better way to write this differential equation is to say I'm looking for an unknown function, call it phi, whose derivative with respect to x is always the function squared. Right? That's what I've always said this kind of differential equation would be saying to you. If it were talking, it would be saying, find me y as a function of x, whose derivative is always equal to the function squared. Y is the function of x, that you don't see an x on the right side, but it's there in your mind. Here, it's not there in your mind. I actually wrote it. A function phi of x, whose derivative phi prime of x is always equal to the function squared. This equation, as long as I'm not dividing by 0, is equivalent to this equation. Divide both sides by phi of x squared, and I'm not really having to multiply by anything. I just did a division. It's not like up here where I multiplied or pretended to multiply by dx to go from here to here. I didn't do any multiplication. I just did a division. I divided both sides by phi of x quantity squared. As long as I'm not dividing by 0, that would be okay to write. I mean, maybe I'd want to assume phi of x is non-zero here, but I won't bother. I've got this thing always equaling 1. That's a function of x. 1 could be thought of as a function of x2, a constant function of x. If these two functions of x are equal, I guess when I integrate them, I should get two equal things too, at least up to an additive constant. Integrate them with respect to x. These two things look different, don't they? Well, at least on the left side, they look different. But guess what? They're really the same thing in disguise. If on the left here, I did a substitution, usually we've used w for our substitution variable, and I did that actually in the first class. Some people always use u substitution. Why not use y? Let y equal phi of x. Then dy is phi prime of x dx, though in deriving that equation back in chapter 7, we initially wrote it as dy dx equals phi prime of x and then pretended to multiply both sides by dx. So maybe this is still confusing. If I'd use the substitution at least it feels a little bit more familiar to say that I guess I can write this as the integral of 1 over y squared dy, or integral of y to the negative 2 dy, which then matches that at least. Okay, so maybe this still feels funny because maybe it's not a proof, because maybe this still feels fishy here. Though we did talk about why that worked back when we talked about substitution. So if you really, really want to know, I don't know, lecture 7 or 8 or something, 9, we talked about why substitution worked. It was actually kind of a similar kind of explanation as to what I'm doing here. In the end, what I'm doing here is I'm showing you, you get the effectively the same kind of integral here, either way you think of it. All right, now let's actually do the integrals. Arrows going everywhere. Do that integral. Okay, we don't get a logarithm on the left time this time. I think in every example, at least that we've done in class to this point, we always got a logarithm, ln of something on the left before. Integrate this, you don't get an ln, you get y to the negative 1 over negative 1, right? Add 1 to the exponent, negative 2 plus 1 is negative 1, divided by the same number. Plus c equals x plus c, and I'll just put the c on the right. Let's call it c1. If we had gotten a logarithm on the left, we'd exponentiate to get rid of the logarithm, but we don't have a logarithm now. We still try to solve for y, though. We still want to find y as a function of the independent variable. Multiply both sides by negative 1 first. Right, y to the negative 1 is 1 over y. I'll do that, where c really is negative c1. Then take the reciprocal of both sides. Flip it. Y must be 1 over negative x plus c, or maybe you prefer that as 1 over c minus x. And there we have what you could label as a general solution. It is a solution no matter what c is. C is arbitrary. It's not quite ideal because it does miss one solution. Notice this right-hand side function up here, this f of y function is 0 when y is 0. So the slope field would have 0 slopes where y is 0 along the x-axis. And the x-axis itself, y equals 0, would be an equilibrium solution. And I will draw it here in a minute. So this one misses that solution. There's no choice of c that will make this function always 0. On the other hand, kind of similar to what happened with the logistic equation, if we call our initial condition y naught and solve for c in terms of y naught, getting c equals 1 over y naught, which is fine to use for c as long as y naught is 0, as long as y naught is not 0. And then plug that back up in here. In place of c, we could write that general solution like this using the initial condition, and then we could do one more step to get rid of the fractions within fractions of multiplying the top and the bottom by y naught, which doesn't change the function because I'm really multiplying by 1, and write it as y naught over 1 minus y naught x. And that is a formula that works even when y naught is 0. So you might call it a better general solution, though I am thinking of y naught as being a specific number. So it's really more like one function if y naught is a specific number. So there we have it. That's probably the best way to write your arbitrary solution in terms of an arbitrary initial condition. The slope field for dy dx equals y squared has 0 slopes along the x-axis where y is 0 and y equals 0 is an equilibrium solution. It's got positive slopes elsewhere, never negative slopes. Slightly positive when y is slightly positive, also slightly positive when y is slightly negative. Bigger and bigger slopes if y gets bigger or if y gets more negative. So solutions up here looks like, I guess, like this. They look like they grow exponentially or something. And solutions down here grow but are concave down. I guess they grow exponentially in the negative x direction. Sort of, I guess. Maybe it's not clear. Yes, this is an equilibrium solution. Is it stable or unstable? It's sort of both. It's approaching it from below and going away from it above. It's sort of like both stable and unstable. Actually, in Diffie with linear, we think about the phase line here instead of a phase plane and call y equals 0 an equilibrium point instead of an equilibrium solution. And we also call it a node. That's the word we use in differential equations with linear algebra. Let me do one more thing with this example to review another topic, review series. Power series, geometric series, and Taylor series all at once, actually, are going to be reviewed. Amazing. This is worth talking about as a preview of something you'll learn if you take the plain old differential equations course. I don't really talk about what I'm about to show you here much, if at all, in differential equations with linear algebra, though I could, but there are just so many other topics that I try to fit in. It's a very full course as it is that I don't have time for this. But in the plain differential equations course, I know Dr. Auk talks about this. Here's your initial value problem. Pretend you didn't know how to separate variables. Is there any other way to solve this differential equation? Yes, you could guess. There are good guesses and there are bad guesses. One actually good guess is to guess a power series in X centered at X equals 0, where the coefficients A0, A1, A2, A3, etc., need to be figured out, need to be determined. Let's guess a solution of this form. Will we be successful? We will for this example. And in Dr. Auk's Diffie class, there are going to be more complicated situations where this kind of guess is pretty much the only way you can try to solve it. So it is a necessary technique sometimes. It's not really necessary for this example, but worth illustrating. The initial condition is going to tell us that A0 must be 1. So that's what A0 is. It's the same as the initial condition because it's at X equals 0. Can we figure out the other A's? Yes, we can use the differential equation. As always, what does the left-hand side and the right-hand side simplify to upon substitution? I will also use the fact that A is 1. The left-hand side is the derivative. Differentiate this. Well, it doesn't matter what A0 is, whether it's 1 or not. The derivative of that is 0. The derivative of the next term is just an A1. The derivative of the next term is a plus 2A2x. The derivative of the next term is a plus 3A3x squared. Then it would be 4A4x cubed plus 5A5x to the 4th plus 6A6x to the 5th, etc. How about the right-hand side? It's y squared. Plug in the function and square it. I got to square a power series. We've done that before. We can do it. Let's go ahead and replace a naught with 1, because that's what it equals. I don't know what A1 is yet. I don't know what A2 is yet. I don't know what A3 is yet. Square that thing, so multiply it times itself. What's my goal? Again, my goal is to figure out what the A's are. Effectively, by setting these two things equal to each other and solving for the A's, if possible. Multiply the infinite series. Take it step by step. Start with the 1 on the left. Multiply it times every term over there. Because it's a 1, that's nice and simple. I get every term over there. I get 1 plus a1x plus a2x squared plus a3x cubed, etc. Then go to the next term on the left, a1x, and multiply it times every term over there, putting the answer in the next row and lining up like terms vertically. a1x times 1 is a1x. I'll put a plus sign here too, emphasize that. a1x times a1x. That's a1 squared, x squared. That coefficient is different than the 1 in the line above it. Go to the next term. a1x times a2x squared. That will be a1 times a2x cubed, etc. Go to the next term on the left. a2x squared times 1 is a2x squared. a2x squared times a1x is a1 a2x cubed, etc. We'll do one more. a3x cubed times everything. If I multiply it by 1, I get just a plain old a3x cubed. And that's the only way you get an x cubed term from there. That goes forever. And then technically speaking, this picture goes on forever and ever. Adding up an infinite series of infinite series. Is this all valid? Yeah, okay, it is valid, but you have to prove that, though we're not. That's left for real analysis. Simplify by adding like terms. The constant term is just 1. The linear term is, when you add these two, plus 2a1x. When you add the x squared terms, being careful, you get a1 squared plus 2a2x squared. Add the x cubed terms, you're going to get 2a3 plus 2a1a2x cubed, etc. What was I doing again? I want these two things to be the same no matter what x is. The only way that's going to happen is if the corresponding coefficients match. a1 must equal 1. 2a2 must equal 2a1. 3a3 must be that, etc. So what do I get from all this? I already knew that a0, a0 was 1. I already knew that. Something new now is I also know a1 is 1. These have to match here and here. a1 must be 1. Something else new is 2a2 must be careful, 2a2 must be 2a1. Look at the x terms. 2a2 must be 2a1. 2a2 must equal 2a1. In other words, a2 must equal a1, which is 1. Boy, we're getting a bunch of 1s here. Does that continue? Look at the x squared terms. 3a3 must be a1 squared plus 2a2. The coefficients of x squared have to match. 3a3 must equal a1 squared plus 2a2. Looking there. Which is 1 squared plus 2 times 1, which is 3. So a3 must be 1 as well. 1, 1, 1, and 1. Does the pattern continue? Yes, it does. A4 is 1, A5 is 1, A6 is 1, forever and ever. All the A's are 1. So y must be 1 plus x squared plus x cubed plus x to the fourth forever and ever. Doesn't that look familiar? I hope. That's a geometric series with leading coefficient 1 and common ratio r equals x. It converges to a over 1 minus r, which is 1 over 1 minus x, if the absolute value of x is less than 1. And hey, that's what we got using separation of variables, isn't it? Compare those two things with y not equal to 1. They're the same. Separation of variables gave us this. Series gave us the same answer when y naught is 1. And it does give the same answer for a general y naught as well, it turns out. And coming back to the slope field, if this is a 1 here, for example, then this is 1 over 1 minus x. It's a function with a vertical asymptote at 1. The solution has a vertical asymptote. Weird, but true. You would not be able to predict that just looking at the slope field. You would also not be able to predict that using Euler's method. In fact, that would be an indication that Euler's method would be very, very bad after just a few steps, probably, depending on how big delta x is. The true solution's got a vertical asymptote. Could that ever happen in real life? Could y go to infinity as x approaches some finite number? Doesn't seem like it should happen. Blows up. It's an example of what you might call a singularity, and it happens in theoretical physics like with black holes. There are singularities. Things blow up in a finite interval, a finite amount of time if x were time. Okay, so just weird things can happen, but we're also illustrating separating variables. We're also illustrating this new technique on using series. I'm not going to test you on the series. Just wanted to show it to you. This is also, by the way, a Taylor series for this function as well. The Taylor series similar to x equals 0. Taylor series are power series. And this kind of power series is a geometric series. Not all geometric series are power series, though, because some geometric series are only numbers, not functions.